Welcome to EDU World Space.
We're given another cross-section that is revolved around the x-axis, and this time the radius changes like k over x, and we know that at x equals a, y equals h, so k must equal a times h. And we can set up our integral. Again, we need to integrate rho r squared over the volume. And the volume is r dr dx d theta, so we wind up with r cubed here. R changes as a function of x, so we have this here. X goes from a to 3a in the figure, and then theta goes from 0 to 2 pi. So again, we can do this integral, plug in, then we get an integral with respect to x, an integrand here with respect to x, do this integral, and then in the end, basically we're going to wind up multiplying it by 2 pi because none of this depends on theta. In the end, we crank through all that and we get 13 pi over 81 times rho a h to the fourth. We can find the volume of this solid by substituting, well, not 1 here, but we'd have r dr dx d theta. So instead of having rho r squared, we'd just have 1, and then we get another r from the area, the differential volume element. And that gives us 2 pi over 3ah squared. Their density is, because it's a uniform solid, the density is the mass divided by the volume. And so that gives us J, the mass moment about the x-axis, of 13 over 54 mh squared. Now we're asked to get it again about the y-axis. Okay, so the y-axis is perpendicular, and this time again we can't just use r squared because the area mass moment about the y-axis is x squared plus z squared, and we know then in polar coordinates z is r cosine theta in the polar coordinates that I've set up. So what we need to do is to change this to polar coordinates, we need to convert this to polar coordinates. We don't have x squared plus y squared, so we can't just put r squared there. It would just be easier for when we add up here. So, but we can set up our integral here, and again we have our integrand here, or our integrand here, and then this is our differential volume element. And go from 0 to r1, from a to 3a, and 0 to 2 pi. We can again crank through this integral, and what we wind up with is pi rho a h squared times the quantity 2a squared plus 13 over 162 h squared. We already calculated the volume, so we can substitute this in here for the density, and in the end we get the mass moment about the y-axis is m times the quantity 3a squared plus 13 over 108h squared. And if we calculate these out for decimals, we get m times 3a squared plus 0.120h squared.